I'm going to review the fluid mechanics section for the FE review. Is this microphone on? Do you have any? Did you turn it on?
It's not in the room. It's just for this.
Yeah, I know. I just don't know if it's actually on.
Oh, yeah, it's on. Yeah.
It's on. Okay, good. Good. So why don't we just start? Some technical issues. I thought there was going to be a chalkboard, and we were supposed to be in Camp 175. So I grabbed this, which I've never used before, but I think I'm okay with that, except that they didn't give me the power cord. So there may be some technical issues somewhat later in the evening. I'm not quite sure how that's going to work. But hopefully we hang on long enough to be all good. That's my plan. Okay, so let's... I can't write like this. Let's see if I can open this. Well, we'll see. No, darn. Okay. Oh, that's actually better. Okay, so this is going to be a pain in the ass. I guess we'll do it like that. That's curious. Let's try that again. I don't know what I did the first time, so we'll see if something better happens.
I don't know how to use a tablet. There.
Ah, crap. Does it work just like that? See that as just everyone rotate their head and we'll be fine. Yeah, I thought actually that's not a bad idea. Let's just do that. Where's up? Okay, now we're good. Okay, so fluid mechanics, how's that? That's coming out the right way. Oh, this is not going to work. When I try to scroll the page, it's going to go whoop. There has to be a button somewhere, doesn't there? Nope. This one looks promising. Ooh, that's promising. Is that better?
All right, we're good.
Okay. Yeah, that'd be good. Thanks. How are we doing now? Yay, okay, good. Okay, don't play with the computer. Super, that's even better.
Look at that.
That is nice. Okay, good. Okay, that's going to be a lot better. Okay, so the things that are covered on the FE exam, you have basic fluid properties. We'll talk about that. You have fluid statics. You have fluid dynamics. And then you have similarity/dimensional analysis. Whoops. Okay, so we'll start with the basics of fluid properties. Right. Yeah. Okay, so basic properties, density. Most people are comfortable with that. Kilograms per meter cubed. Specific weight, which is basically just rho g. So sometimes they'll talk about specific weight. That's just rho g. Sometimes they'll talk about, specific gravity, which is SG, and it doesn't have a symbol. There's no symbol for specific gravity other than just to say it's specific gravity. Okay. Well, it's really not easy to write hunched over like that. I think I sort of need to be standing.
There's a whole row right there.
What's that?
There's a whole row right there.
Yeah, maybe if you can't see and move, because otherwise I can't. I mean, I could move myself off to the side. That might be okay. But then we have other issues, so we can't do that either.
That's the longest cord I've got.
Okay, so we're stuck like that. Okay, specific gravity is the ratio of basically gamma to gamma something else reference. And typically the reference is water. So it'll be just the ratio of, it's really the ratio of density to density of water. So specific gravity of beer is slightly like 0.9. It's less dense than water, and specific gravity of salt water is slightly less than water as well. So they often give you specific gravities in questions. One property that they will maybe ask you about, which isn't covered so thoroughly in the fluid mechanics classes you've taken, is surface tension. And so that's basically newtons per meter. And so it's a tension. It really is a tension. And if you have problems involving surface tension, you can almost pretend that it's like a little cord with some tension in it, like a rubber band. And that's the way to handle those. Just treat it like a statics problem with a rubber band in it. And then you can handle surface tension. And the tension is basically newtons per meter. And so we'll do some questions with surface tension in them. What else do we have here? Viscosity, kilograms per meter second. We'll talk about what that is. Oh yeah, there's also kinematic viscosity, which is just mu over rho, and that has units of meters squared per second. Okay, yeah, I don't have to talk about that. Yeah. Good. Okay, that covers that. Yeah, I'm going to try to figure that out in a second. What happened there? Oh, there we go. Okay. Too far? You want me to scroll back a little bit? Okay. Okay, good. Some simple formulas that you'll be expected to have in your mind before you do anything else is other ones is shear stress, tau xy, and that's equal to mu du dy. Mu is the viscosity, u is the velocity. Whoops, sorry. And y is vertical distance. And so when you want to evaluate the shear stress on something, it's the gradient of the velocity in the direction perpendicular to the surface. And so we'll do an example with that too, some simple examples with that. The units of this, tau xy, is a stress. So it's a stress, so that's newtons per meter squared, which is the same thing as a Pascal. And pressure also has the same units as that, so this is also pressure. Okay. Okay, that covers that. Good. Some other simple formulas. Let's see here. Simple formulas before we start to do hydrostatics. Maybe we do let's do a quick shear stress problem. So a typical problem would be, okay, a bearing. So this tau xy is the shear stress between two sliding surfaces. And so you might have a bearing like this. And the questions aren't horribly complicated, but you just need to know the fundamental concepts. And maybe you would have u moving this way. So this is a plate. And you could think of that as some sliding bearing. And then you have some liquid in here. This one's moving. This one's fixed. Okay, and then you have a viscosity here. And they could ask you, okay, let's say I give this a certain, let's give the plate, so this is in 3D, it looks like that. So the plate has a certain area. Okay, so I'm just dragging a sheet of paper across a fluid, basically. And I ask, well, how much force is required to drag that plate or that bearing or whatever it is? And so basically, the only thing you need to know is that the velocity profile here is linear. Okay, so you have a linear velocity profile. And that means that And if this distance is d, right? So somehow you know that distance. How am I doing? Does it get too low when I get down there? Not quite sure what to do about it. So then we have basically delta u is u minus 0. Delta y is just d. It goes from 0 to d. And so that's equal to du dy. And tau xy is just equal to mu du dy. So that's mu times u plate. I'm going to put a p on that just so we can be clear on that. Mu plate over d. So that's this pressure. That's got units of newtons per meter squared. And so if you want force, you just multiply by area. And so the force that was required is equal to basically tau xy times a. Okay? And that question might appear in various ways. It may be, okay, there's a viscometer, which is a device for measuring viscosity. And they tell you the force, and they tell you the gap height, and they tell you the speed. And then you back out the viscosity, so that would be one way. Or the reverse, where they give you the viscosity, and they tell you this, and they tell you the speed, and you calculate the force. So one of those simple kind of questions with that thing. Other things before we go to hydrostatics. Maybe it would be good to do a little surface tension, because I think you're probably less comfortable with that. Yeah? Okay, so surface tension, there's really just two surface tension problems you'll get. Surface tension is a problem is important in two basic problems. One is bubbles and drops. Okay, so you have a liquid here, a gas here, and there's a surface tension sigma. Okay, and let me just make sure I don't mess this up. Yeah. The difference in pressure, because it's a balloon, essentially. It's a balloon. You have a tension around the balloon. And because there's tension, the pressure in the balloon is higher than outside. Yeah? And so the formula to remember is delta P is basically equal to sigma. Now, sigma, remember, has dimensions of newtons per meter. So if you're having trouble remembering, it's newtons per meter. And you want to get something with units of pressure. So it's sigma over basically r over 2. Whoops, that's the radius. Sorry, over 2. Okay, so that gives you the delta pressure between the outside and the inside of a bubble, a drop, any sort of gas inside of another gas or liquid inside of something with an immiscible interface. Okay, so that's the one sort of surface tension question you'll get is just, okay, you have a bubble and what's the pressure jump across the bubble? This r is the radius of curvature, so for a sphere that's just r. Yes, that's simple. The other sort of important surface tension question that you'll get really has to do with manometers and how you read a manometer. So everybody is familiar with the problem of taking like a straw and sticking it into a fluid, and they have capillary action and the flow goes up the straw. Yes. So the way that works is something like this. Let's see if I can move down. I guess that's okay. So here's your straw. And now here's this meniscus inside the straw, okay? And here's the liquid sort of outside the straw. So this is atmospheric pressure. And this up here is atmospheric pressure, okay? And so now you have this sort of weird thing where the water is basically climbing up the inside of the straw. There's another property that's important, which is essentially a property of a liquid and a solid, the interaction between a liquid and a solid, which is the contact angle. And so this angle is theta, is called the contact angle. Whoops, contact angle. Okay. Juchek exec is requesting what? Cancel. There. I don't know what that is. I don't know what it's for. Okay. So what happens? Think of the meniscus as a rubber band. And so I'm going to draw a control volume. And so I draw a control volume and I cut through Okay, so I draw my control volume like that. And what is the pressure on the bottom of my control volume? This is a hydrostatics question. The straw is open on the bottom, so when you go across any horizontal level in a fluid, in a hydrostatics problem, the pressure on every horizontal level is the same. So that means that the pressure here is atmospheric, and the pressure there on the top is atmospheric. So there's no net pressure force on this little piece of fluid in the straw. Okay, so the net pressure force is 0, so I don't have to account for that. And what's happening here is this. Here's a redraw of that diagram. Surface tension is like a rubber band, and so that is pulling this way and that way. Okay? This angle is theta. This angle is theta. Okay? And it depends on whether this is a straw or a channel. I can make it axisymmetric. The net force here, due to that thing, let's make it a straw, so we'll make it circular. Sigma, if you think about units, is newtons per meter. So if I want a force, I have to multiply by something with units of distance, right? The distance here is the circumference, because that's where I've cut around. So the force up due to surface tension equals sigma times 2 pi r. Okay? And the force down, what's that opposed by? So the down force that it's pulling things up, what's holding it down? Gravity, right? So gravity's holding it down. And so basically this height, which we sort of roughly approximate, is the weight here is the height up times pi r squared times what? Times rho times g. And so we set that equal to sigma 2 pi r. And given the diameter of the straw, the density of the fluid, and the surface tension, we can solve for the amount of the height that it goes up and down the straw. Okay? That's somewhat clear? And so I would solve for h, and h is just going to be equal to sigma, the pi's cancel, 2 over, I need to move down. What am I doing here? We get an r rho g on the bottom. Yeah. Okay, 2 sigma over rho g r. And that's the amount of height that you go up in a capillary tube. And we'll see why that's important, because when you read manometers, there's always an error because a manometer is a little round tube, and the liquid will just climb up the tube and give you an incorrect reading. Okay? Okay, that's surface tension, so that's a little review of that. Okay. All right, so now we're going to move on to the next topic, which is fluid statics. All right, so basic idea of fluid statics. Fluid statics is obviously a fluid that doesn't move. And so you would say, okay, P1 minus, whoops, how do I undo? Oh, yeah, I remember. P1 minus P2 is equal to minus rho g Z1 minus Z2. Okay? So that's your basic formula. It tells you that as you move down in a fluid, so if Z2 is less than Z1, let's see, did I do that right? Yeah, Z2 is less than V1. This is negative. That means P1 is less than P2. Okay? So you go down in hydrostatic pressure. Or as you go down, hydrostatic pressure increases. That's the basic formula. What do we want to do with that? Let's do, yeah. Okay, so there'll be a lot of manometer problems. Everybody knows what a manometer is? You know what a manometer is? Yeah, it's a little glass tube with some heavy fluid in it that shifts depending on the pressure differences between the ends of the tubes. So there'll be manometer problems, and they'll look like this. This is an example. Whoops. Let me erase a little. So maybe here's an example where there's some sort of, I don't know, a valve. That's a pretty crappy looking valve. Yes. There's flow going down the pipe. And you set up this experiment, and you want to basically see, well, what's the pressure difference caused in the pipe by the valve? And say, OK, well, I need to know the pressure difference from the front side of the valve to the back side of the valve. I tap the pipe onto the side on the left and the right, and I fill this with some fluid which is heavier than the fluid that's in the pipe, because if it's not, it'll just get flushed out, right? And so I fill this with something like mercury, although that's probably not health conscious, but that's all right. It's a nice heavy fluid. And this side will have, there'll be a high pressure on the left, right? So this is high pressure. There's low pressure on the right. So the high pressure will push. I don't know where that just went. You'd think there'd be an undo button, wouldn't you?
Right under the table.
Where is it?
All the way at the top, it says table.
Table, undo. Got it. There's my drawing. Super. I'm not sure what button I hit, and I'll try not to hit it again. OK, so.
You know what it is? If you press and hold, I think it deletes.
Press and hold?
Like if you press down and leave it there.
Really?
Yeah, it brings up like a menu option.
OK, there we go. Don't draw too much on that. I'm not quite sure what's going on there. And so, OK, we'll get a difference. There's a difference in height here. OK, and we'll call that, I'll call this 0.1, and I'll call this 0.2. OK. Some basic rules of hydrostatics. I drew this line this horizontal line across it. If I'm in the same fluid, and the fluid is connected, meaning I can get from one spot to the other by moving through the fluid, the pressure is always the same on a horizontal level. So even though I'm going down, back over, and across, the pressure here is exactly the same as the pressure here. It doesn't like that spot. Yes, everybody understands that concept? Yeah, OK. You can go horizontally in any fluid. As long as you're in the same fluid, it's fine. Other simplifications when you look at these problems, they're not going to give you this dimension. They won't tell you what this is, the dimension from the side of the pipe to the top of the mercury. And the reason they won't is because the pressure change is the same on both sides. So the net effect of that is 0. It doesn't add to the pressure difference. You see what I'm saying here? Meaning, if I want to know the pressure difference from here to here, well, this little glob of water here and this little glob of water here, I don't know how to point well while I'm talking. Can you, when I poke on the screen, do you get what I'm talking about? OK. So those little globs of water don't do anything. They don't add or subtract anything because they're the same on both sides, the net pressure difference. And so I only have to worry about points 1 and 2. And so I can go down and say, all right, what I'm going to do then is make a loop. I'm going to go from 1 down to 2 in the water. Horizontally across is no big deal. And then 2, and I'm going to call this point, this is also 2. So I'm going to label that 2, 2. And I'm going to label that 3. So I'm going to go 1 down to 2, 2 to 3. And I just write 2 hydrostatic equations for this. So I say P1 minus P2 is equal to minus rho G Z1 minus Z2. And then I like to write all the equations in order, so I stack them all up on top of each other. So I'll go now, and I put the points in the order that I'm going to go. And so then I would say, OK, I'm going to go 1, 2, 2, 3. So the next one is P2 minus P3 equals minus rho G Z2 minus Z3. OK. And then I really don't care about the intermediate pressure P2. So I'm just going to add these two equations together. I sort of stack them all up and then add them, and I see what I'm left. And I say, okay, this is P1 minus P3 is equal to, and I forgot the subscripts, 1 to 2, okay, is water. And 2 to 3 is mercury. Okay, so I have slightly different things there. P1 minus P2 minus P3 is minus rho G H2O. Whoops, darn it. Z1 minus Z2 is H, yeah? So minus rho H2O G H minus rho Hg. Okay, now I have to be careful. I have Z2 minus Z3. Z2 is less than C2. That's minus H, okay? So this becomes minus H. And now I have a formula, and there's a G. And so now I have a formula for P1 minus P3 equals Y. There we go. Okay. And so now I have basically the manometer. I have the reading of the manometer. That's the pressure difference between the upwind side or the upstream and downstream side of the thing. Yep.
You have points 1 and 3
Yep.
on the same horizontal line. Is that to indicate that the loop is closed or because they're on the same?
They're on the same horizontal line. Let me go up so I can see. So 1 and 3 are on the same horizontal line. And because, if I move up 1 and I move up 3, I'm adding this little section of water. When I add the water on the left and add the water on the right, they cancel. So I can shift that line right to where I want to know the pressure difference, and it doesn't do anything to my pressure difference. So I don't need to know how far down. In fact, they'll often not give you that distance, which will confuse you. They don't give you how far down the water, the mercury starts, because it doesn't give you a net pressure. Also, in this kind of problem, the capillary effects are not important because there's a capillary effect on the right and a capillary effect on the left, and they cancel. So you don't have to worry about it. Okay. Okay. Let's see what else we're doing here. Okay, so that's a big part of the problems is the manometer stuff and just knowing how to read a manometer and calculate those things. What else we got? Okay, so we're getting into hydrostatics. There's something else I just saw that I needed to tell you. What was it? No, not that. Oh, yeah. Okay. Before we do forces and things due to hydrostatics, one other sort of important little rule that they'll ask you about. Is buoyancy forces. Buoyancy. Oops. It doesn't like this thing. There we go. Buoyancy forces. The basic rule is that the buoyancy force F is equal to the weight of the volume displaced. And so I have this totally retarded weird problem that was on the exam, so I'll show you that. It's a ball. Now, I don't know why anything like this would exist in real life, but that's a different story. And it's sitting somehow miraculously exactly at the halfway point between, this is open, so this one is like oil, and this is water. And this thing has a radius r. And they ask you, and this is a ball of mass m. So maybe it's, I don't know what the mass of the ball is given. I don't have the numbers, so it's not really all that important. And so you have this ball hanging on a string, sort of floating in water. Yeah, and the ball is like a golf ball. Yes? totally artificial problem that no one in their right mind would ever actually do in real life, but nonetheless, this is the kind of things sometimes you get asked. And so they ask you what's the tension in the, what's the force in the string, okay? So how do you do that? It's really quite, it's pretty simple. It's just, again, buoyancy. Even though it's complicated, it seems complicated in this problem, buoyancy force is equal to the weight of the fluid displaced. And so the buoyancy force, F buoyancy, well, half of the water, half of what's displaced, the water is supposed to split the sphere in half the way I drew it. And it's okay. So half of it is 4/3 pi r cubed divided by 2 for the half of a sphere times the density of the water times g. And the other half is in the oil, so that's okay, so that's the buoyancy force. And then you just do a force balance on the whole thing. And you say F buoyancy. Wow, I really can't write that word. F buoyancy minus the weight, which is just mg, equals 0. Oh, sorry, that doesn't equal 0. Plus the tension force equals 0. And then you just solve for the tension force, okay? So that's a buoyancy type problem. Okay. Yeah. All right, so now we're going to do hydrostatics. Well, this has all been hydrostatics, but this is hydrostatic forces. Okay, so hydrostatic forces, there's basically forces. This is all going to be forces on flat plates. So things to know, let's see here. What's a typical problem? Would be, you know, here's a dam. And what's the force on the dam? Okay. So this is a terrible room for doing this. Sorry. So we have, you know, forces on flat plates, basically. And so the one important formula is that the force is equal to the pressure at the centroid times the area. Okay? Now, you probably are, I don't know if you remember this at all, but there's, if you think about the pressure distribution on this thing, let me do just a normal plate. This would be the pressure distribution. Say it's a submerged plate. And you know, that's just the rho gz sort of linear growth in pressure because of the hydrostatics. And so all you do really, if you think about integrating force, you have this line which goes from, it's a linear profile which goes from a low pressure to a high pressure. All you do is take the average pressure and multiply by the area. Okay? And the average pressure is the pressure which occurs halfway, the centroid. So you evaluate the pressure at the centroid, multiply the area, that gives you the force. Yeah? Okay, so that's basically it. So this thing, if I take this plate, and I have to do each plate separately. I can't do everything simultaneously, although in this problem I'll show you a cheap way to do this quicker. Because the pressure, because the direction of the force will change, you have to do each one at a different angle separately. Okay? So here I'm going to have a force that looks like this. Here I'm going to have a force which looks like this. And for now, we'll just calculate the magnitudes, and then we'll talk about center of pressure, which is a slightly different concept. Okay? Center of area and center of pressure. Well, there's the centroid, and then there's the center of pressure. Those are two different things. Okay, so yeah. Okay, so how would you do this? Let's give some dimensions here. This distance would be h1. This distance would be h2. Okay. And okay, I want to know the force on the dam, so I'll do h1 first. There's some trickiness to this. When I evaluate the pressure at the centroid, the only thing that matters is the vertical distance downward. And so h1 is vertical, h2 is vertical. So the pressure at the centroid, P centroid, I'm just going to do the top plate, and we'll not worry about the top and bottom plate, is equal to, okay, well, okay, let's do that. Sorry, getting confused. Let's just do it a little bit cleaner than that. So the centroid, Z centroid is equal to basically h over 2 minus, because it's down, and we'll set Z equals 0 at the top. Okay, so this is Z equals 0. The centroid position is minus h over 2, h1 over 2. Okay, now we just calculate the pressure at the centroid using our formulas. P1 minus P2 is equal to minus rho g Z1 minus Z2. Let Z1 equal the top. Let Z2 equal minus H1 over 2. And so then we say, okay, P1 is, and typically these problems, I'm not totally sure. I think in general, I'd have to check this. You use gauge pressures. Let me just double check to make sure that I'm right about how they ask you these things. Yeah, typically you'll use gauge pressures. And so that means you can just ignore the atmospheric component of this and essentially set atmospheric pressure to 0. Okay, so use a gauge pressure. So we'll say, okay, P1 equals 0, because that's atmospheric, and atmospheric at gauge is 0. So we have 0 minus P2 equals minus rho g. Z1 is 0. Z2 is minus h1 over 2. So minus minus becomes plus. Okay, and then if I monkey this around a little bit, P2 is equal to rho g times h1 over 2. Now I have the pressure at the centroid. Okay, so that's the pressure at the centroid. And then to calculate the force on the plate, I need the area of the plate. Now that's the only thing that's tricky about that is that in this case, because the plate is angled, the area of the plate is, and this is going to be some depth into the page, which I have to think about. But if I'm given like this being some distance, I don't know, h, what is horizontal? L. Okay. Then I would use basically, and let's give it a depth d into the page. Okay, so then my force is equal to the pressure at the centroid, rho g h1 over 2, times the area of the plate, which is square root of L squared plus h1 squared, times the depth into the page, d. Okay, and that's the force. So that's the area of the plate. Everybody with me on that? It's okay? And just taking the length of the plate and then multiplying by the depth into the page. Hard to know if everybody's with me or not. Okay, so that's that. That's how you calculate forces. There are, I don't know if they do this or not. Let me just check the book to see. I can't remember if there's any questions about centroids and centroid locations. Because the pressure distribution is not uniform, it increases with depth. The location, the line of action of the force is not at the centroid. So that's the somewhat confusing part. You calculate the net force using the pressure at the centroid, but the line of action of that is below the centroid. Got that? let's see if I can just double check to make sure that I don't think that they really get that detailed. I hope not. Yeah, it seems that they don't ask too much about the centroid locations. Oops, yeah. So I don't know if I need to go into that or not. I think I will leave that out. Oh, well, maybe I better tell you. Okay, so centroid location. Well, actually, it'll be, okay. Yeah, it's basically, I haven't done this in so long, I forget. There it is. Oh, okay, let me get it right. Sorry. Let me get this just right. Here we go. Y minus y centroid is equal to rho g sine theta Ixx divided by the force. Okay, that's the simple formula. Y minus y centroid is this distance. So if the plate has an angle theta, and here's the centroid, right? That's halfway down the plate, and this should be minus, I think. Y minus y centroid. Yeah, it should be minus. This distance, this is y centroid, and y is measured in the plane, so this is the y direction, okay, along the plate. And so this is y centroid, which is somehow the middle of the plate. Yeah, that's the one we've already figured out. But this is measured in the plane of the plate. And y, this is y center of pressure, is somewhere down here. And so you already know how to calculate the force. Rho g sine theta is easy, okay? And Ixx for a rectangular plate so it's the this is the base is the depth into the page. So B is depth into the page. And this distance is L. Okay? So L is the length of the plate in the plane of the plate. B is the depth into the page, the horizontal distance into the page. And that's how you calculate Ixx, is just 1/12 the base times the height cubed, multiplied by rho g sine theta. If the plate is horizontal, that means theta is 0, and the center of pressure will be exactly at the centroid because there's a horizontal plate, the pressure is uniform. If the pressure is vertical, the center of pressure will be below. And the center of pressure will be below because there's more force below the centroid than above. Okay? Questions about it? It's okay. Okay, maybe we'll do an example of that. Yeah, I'll pick a review example and we'll do one of those. One thing I was going to tell you, which I've totally forgotten. I can't remember what I'm doing. What was I going to tell you? Something else. Oh, yeah. Okay, remember. It's been a long week. Some little tricks before we do an example. Sometimes they'll draw a dam like this and say, you know, what is the horizontal force on the dam? So here's my dam, and it's holding back this water. And wouldn't you know, it's not a flat plate, yes, which is highly disconcerting. So what do? You sort of say, well, I'm going to pick this as a control volume, okay? And the net force on that hunk of liquid has to be equal to 0 because it's not going anywhere. And this is a nice flat plate here. This is gauge pressure, so there's no pressure force on the top. This is the force I want to calculate on this surface. And the other thing I have is weight. But weight acts vertically downward, so I don't have to calculate that, right? So in that case, I can just calculate the force on this flat plate, and that will be equal to the horizontal force on the dam, okay? And if I want the total force, then I have to calculate the force on the flat plate plus the gravity force, right? So if I say, here's the force of the dam this way, force of the dam plus the weight plus, let's call this AB, equals 0. And now I just have to do a flat plate problem. I calculate the weight, and now I have the net force of the dam. Okay? And the weight can be tricky. Maybe this is typically, if it was, I don't know how complicated they'll get with this, but if it was, the weight would be, you would have to calculate the volume of that area, multiply by the density, multiply by the gravity. So in this case, maybe it's a quarter circle and a rectangle or a square, and you can calculate the area of that, multiply by the depth into the page, multiply by density, multiply by gravity. That gives you the weight. Okay? So those are a tricky, if you see a curved thing, immediately think about slicing something with a flat plate and using the flat plate formulas, because you're not going to be able to calculate anything on a curved surface within the time of this exam. Yeah? Okay, so is this okay? Do you want to keep going, or do you want to see a quick example with hydrostatics? Everybody, I don't know what you want to do. Tell me what you want me to do. Quick hydrostatics example from thing? Okay, we'll do a quick one. I'll pick one from this little example thingamajig. Yeah. Okay, so we'll do this one. This one is very simple. It's not too hard. Okay. Yeah, okay, so we'll do that. So it's really the one I just described. It's basically this and this. That's your dam. This distance is 30 meters. This distance is 20 meters. Vertically 20 meters, vertically 30. What else do they have? And they say, okay, this is the cross section. Okay, they give you some totally useless dimensions. They make it look like that, or something like that. I don't know, it looks a little bit like this. And they tell you this distance is 30 meters, and this distance is 20 meters. Okay? And they say, okay, actually, yeah, it's 20 by 20, so that's a 45. And then they say, what is the magnitude of the resultant water force per meter of width acting on the face of the dam? So force per unit depth on dam. Okay. Okay, so could do this two different ways. One is just to do it directly, calculate the force on this top plate. And in this problem, there's nothing about the line of action of the force, so that's good. You don't have to worry about anything about the center of pressures. All you need is to know is the magnitude of the forces and the directions. Okay? So you could do it that way and calculate those two things. Another thing you could do is just calculate it on that one plate and then add in the two weights. So either way would give you the answer. I prefer to do the quick and easy way, I guess. So let's just do the one where we do it like this. We say, okay, force of dam plus weight plus FAB equals 0. This is A, this is B. Okay, the centroid of side AB is at what height? 25 meters, right? Because it's 30 plus 20, and I'm just treating the whole thing as one big plate. And so halfway down is 25 meters. And being a little quick about this, I know the pressure on the top is 0. And so I'm just going to say rho g h over 2 is the pressure at the centroid. So P centroid is equal to rho g times 25 meters. Okay. The area per unit depth of this plate, well, it's nice. I mean, because it's purely planar, I have 30 plus 20 is 50. That's my area per unit depth. Yeah. So I have times, so FAB equals the pressure at the centroid times 50 meters. Okay, that's FAB, that's done. And that, we should keep track of I and J directions. So this is purely in the I direction. How do I know that's in the I direction? Because pressure always acts normal to a surface. And the surface I've drawn is vertical. Pressure always acts normal to it. And so that's a horizontal force. Okay, so that's horizontal. The weight, well, I have two weights here. I have this one and I have this one. They're both vertically downward, which is nice. And I don't really need to know the locations of them. I'm just interested in summing everything up. So I have weight equals, okay, this one is a square of, oops, yeah, it's a square. It's not a square. It's a rectangle. It's got a height of 30 and a width of 20. Yeah? This rectangle is 30 by 20. So it's 30 by 20 times rho g, and that's in the j direction, minus. And the triangle here, well, the triangle is actually half of a square because it's a 45-degree angle, right? See, it's a 20 by 20, so that makes it, the area of the triangle is just half base of height anyway, but it's basically 1/2 of 20 times 20. And that's also in the minus j. And now I just plug everything in, and I have the force of the dam, the net force of the dam. And they give you choices like A, 7.85 meganewtons per meter. So it's force per unit depth, so it's newtons per meter. And I would just take, I have an I and j component. I'd square the I component, square the j component, take the square root, and that's the magnitude of the force. Yeah? It's okay? Okay, let's see what else we're doing here. Yeah. Okay, I think we're good for statics. Let's see if I've missed anything here. I don't have an example where they actually ask you to calculate things with centroids. Forces on submerged surfaces. They talk about it, certainly. You know, one way to know if you're going to need to know about centroids is if there's a hinge or some sort of weird gate in the problem, they're going to ask about moments. So as soon as you see a hinge, a pin, a gate, it's a moment problem. And that means you're going to need to know the line of actions of the forces. So if you see that in a problem and you see there's a hinge, immediately you think moments. Immediately you have to think, okay, I'm going to have to calculate centroids. Okay? If they just ask for the magnitude of the force, the net force, the direction of the force, you don't need to know anything about centroids. Okay? Okay, let's keep going. Let's talk about fluid dynamics now. So first, conservation of mass. Most of your problems are going to be fairly simple, just m dot in equals m dot out. Sum m dot outlet minus sum m dot inlet equals 0. M dot is rho times Q, where Q is the volumetric flux. And Q is equal to the velocity in the normal direction. So typically the velocity will always be in the normal direction, so I can just write down V and not be very explicit about saying that it's not a tangential velocity. It's just a normal velocity. So velocity times area. Okay, so those are your basic formulas for conservation of mass. I think that's pretty straightforward. Conservation of momentum would be next, and we'll do some problems with this. And again, all of these will be written in a way that you can do them fairly quickly. And so the simplified formula looks like this. Sum m dot v out minus sum m dot v in. So this is outlets equals the sum of the forces. Okay, that's the basic equations. We'll do that in a second. Let's do an example of this. Typical examples are, typical problems with this will be like flow through a bend. Okay, so you have a flow turning, and they want to know the net force because of this, like a water faucet. So yeah, something like this. You have flow coming in at this thing, and I can even make it mildly complicated if you want. It goes through a 45-degree bend, and then it goes into a nozzle and sprays on the ground. Okay? And there's a pressure measurement here. And what's the pressure at the exit? Atmospheric. It's a very almost universal assumption that any exit, you just assume it's atmospheric pressure. So here, P equals P atmospheric. Okay, this is, whoops, well, no, how about this? It's 45 degrees. There are some bolts right here holding this thing to the wall. Whatever, I don't know why, but that's what's happening. And they ask you what's the net force in the bolts, something along those lines. Okay, so here we go. And well, we'll just tell you something about the inlet velocity is 25 meters per second. So it's a good water jet of something. Inlet diameter equals, let's make this big, 10 centimeters. And then it comes down to this little nozzle, which is D equals 1 centimeter. And so there's a nice complicated problem that would take a lot of time to work out, yes. Okay. Okay, so first of all, I have the diameter at the inlet, I have the velocity in the inlet. What does that tell you right away? Yeah, it's the mass flow. So I have diameter and velocity at the inlet, so I can calculate Q is equal to pi d squared over 4, which is the area, times the velocity, which is 25 meters per second. And d in this case is 10 centimeters, so we could just plug that in. I'm just going to call that d inlet. Okay, and this is Q. And why do I calculate Q? Why am I bothering to do that? So I can get the velocity on the outlet, because it's not specified. And so I need the velocity in the outlet. So first, every problem like this, there'll be a mass conservation part first, and then a momentum conservation. First you use mass, then you use momentum. And so, okay, first we use mass. We're given velocity at the inlet. We calculate the velocity outlet. Let me write that. Q outlet equals Q in equals pi d out squared over 4 times the velocity out. And so pi d in squared over 4 times u in equals pi d out squared over 4 times u out. And we just have u out over u in is equal to d in, oops, did that wrong. U out over u in. Yeah, d in over d out squared. Did I do that right? Yeah. Okay, that's good. So this ratio in this particular problem is d in is 10 and d out is 1, so this is equal to 100. So I've made the problem totally ridiculous. The velocity is coming out at 2,500 meters per second. Yes? Whoops. Okay. I hope we have big bolts. That's all. Okay, so that's the velocity out. I have that. Okay, then I look at my conservation equation. I have sum of the forces. I have m dot v out, m dot v in. I have the m dots now. M dot in is equal to m dot out, so I have that. V out, there's a vector sign over the v out, and there's supposed to be a vector sign over the v in. It's important that you remember that. Okay, so let's just do that part. So I really have now m dot equals rho times pi d in squared over 4 times u in. Okay, so that's m dot. In my momentum equation, since m dot in is equal to m dot out, I can just factor out the m dot. And I say, okay, m dot times v out vector minus v in vector equals sum of the forces. Okay, so we can plug in stuff here. So let's finish the left-hand side. M dot v out is 2,500 meters per second, but it's at a 45-degree angle. So I have to do the vector components here. So this will be 2,500 times the square root of 2 over 2 in the I minus 2,500 times the square root of 2 over 2 in the j. And this would be cosine theta sine theta if it wasn't 45 degrees. It's just that this is 45, so it's easy enough. But you could use cosine theta sine theta. Yeah. And then minus v in. Now v in, whoops. V in was 25 meters per second, and it's horizontal. So that's just minus 25 in the I equals the sum of the forces. Okay, so now we have to work on the forces. Tell me about the forces here, which are the ones that we... And so let me draw the control volume because I didn't really draw it, and I want to draw it in a way which makes this easy. I'm going to cut through the pipe here, and whenever I cut through the metal, that means there's a force there because the metal transmits force, right? Plus I'm cutting through the fluid here, so I have forces all along this side. Then I go around the outside of the pipe. What's good about going around the outside of the pipe? No fluid forces. I assume everything on the outside of the pipe is just negligible. If it's in gauge pressure, I don't have to calculate any of that, right? So I go around the outside of the pipe. That means there's no forces on those sides. And then there is a force where I cut through the fluid on the far end. Okay? Maybe. So we'll see about that. Okay, so some of my forces will be, first, the force of the bolts. Okay? I've missed one thing, too, when I was in that discussion. What's the other force that's involved here? I cut through the bolts. I have the force at the fluid on the right, on the left. I have the force on the right. There's also a weight. But if they don't specify volume and they don't specify anything, that means that they're not giving you enough information to do that, and you just ignore it. Okay? So I say, okay, I don't have any information for that, so I forget about it. Okay, force of the bolts. And so now I have, how about the pressure force on the outlet? What's that? What's the gauge pressure at the outlet? 0. So there's no pressure force on the outlet. I don't have to calculate that. All I have to do is calculate the pressure force on the inlet. Okay? So I have, in the direction of the pressure force on the inlet, this is the forces on the fluid. Is it to the right or to the left? It should be to the right, yeah, because it's the forces on the fluid. And I'm doing conservation mass for this glob of fluid. The pressure is pushing on the fluid to the right. So I have plus P1, comma, gauge. Pi d n squared over 4. Can you move this horizontally? Ooh, you can. Okay. And that's in the plus I direction. Okay, so on the inlet, I have the gauge pressure, which is just taken from this gauge, which I was assumed given, right? This P1 gauge is given. And so I just take that pressure, multiply by the area, and say that's in the positive I direction because it's a vertical plane. Okay? And that's enough. Now I can solve for the bolts, the force in the bolts. Okay? Okay, good. Let's see how we're doing here. Not too bad. That's the conservation of momentum problem. You'll see a couple of those on here for sure. What else? Okay, mechanical energy stuff. We'll talk about that now. Yeah, talk about mechanical energy. So you guys are familiar with the concept head, pressure head is the way that this is termed, and H is defined as, this is H, meaning H is a length scale. It's a totally confusing unit to students because it's really a pressure, but then we divide by rho g and call it a length scale. And so you can think of it as the amount of pressure, you would think of it as the pressure, the height that a pressure could cause the fluid to rise. That's what the head is, okay? So head is basically P over rho g plus 1 over 2g v squared plus z, which is the vertical distance. That's the definition of head. Okay. And the fundamental sort of equation that we use here is H2 minus H1. So 2 and 1 are two different locations, is equal to the head loss in between those two spots. Plus any head provided by pumps minus any energy taken out by turbines, which is whoops, I can't spell. Okay, so that's the fundamental equation, is the change in head is equal to the head loss plus any pump energy that's put in minus any turbine energy that's taken out. And there is a relationship between, so head associated with the pump is equal to the efficiency of the pump, and we'll talk about that slightly, times the power put into the pump divided by the mass flow rate times G. Okay? So that's the pump. And typically, the way you measure power in a pump is you plug it in and you measure how much current and voltage is going into the pump. But if it's a crappy pump, it doesn't do that much work on your fluid, and so that's why eta is there, right? So eta will be a number less than 1. If you have a shitty pump and you plug it in and you consume 300 kilowatts of energy, it may only be doing 20 kilowatts of energy on your fluid, so you have a low efficiency pump, yes? And turbines are defined sort of the opposite of that. W dot turbine is the amount of power that you pulled out of a turbine. And you could pull tons of fluid power out of the fluid and have a crappy turbine and get a really trickle of little power out of the fluid. So W dot turbine is equal to, how do I write this? Let me see if I've got that. Yeah, the efficiency of the turbine. Okay. Okay. Let me read it right this way. So we're symmetric here. H turbine equals W dot turbine. And that's the W dot turbine is the power you measure electrical power out of the turbine, right? But you divide that by the efficiency because you're actually going to have to pull a lot more out of the fluid times N dot G. Okay. All right, that's that. Yeah. Good. Okay. Let's do an example with that. Losses, what are head losses? Where do they come from? So head losses will be frictional losses from piping. So you have, we'll talk about the Moody chart and the frictional losses. Head losses are from valves, elbows, corners, blah, blah, blahs, sudden expansions, sudden contractions. And they'll all be little, nice, cute little correlations for head losses, yes? And so we have all this stuff for head losses. And so let's do a problem with that. Let's see here. Do I have something? Well. Okay, let's do, how about this one? I'll make something up. Although mine made up problems don't seem to come out so well. I got one anywhere? Come on. Statics, friction, pipes. Oh, well, I'll just make one up. I can't find a good one in here. Let's do, oh, there's one right there. Yeah, okay, this one doesn't have a pump in it, though. I want to put a pump in. All right, let's do one like this. So you have a reservoir here, and it's a big reservoir. It's connected by a pipe. There's a pump. Yeah. And it's sucking water from, actually this is a water tower. There we go, that's better. And that's a lake. And that's an overly large pump, yes? Okay, something's happening there. Okay, and now I don't know what's the best way to ask this question. What am I even going to ask? Let's calculate something. How about, that's awfully complicated to ask it that way. Okay, let's ask how much power is required. Okay, so what power required by 90% efficient pump to, and we'll do this problem twice, I think, to move, and we'll pick a volumetric flow rate. So I'm going to say maybe we pump a meter cubed per second. From lake to water tower. Okay, so that's the basic idea of these kind of problems. And so we have to pick, these problems will always be from one point to another, so you have to pick the point 1 and the point 2. The point 1 and the point 2 are sort of obvious in this problem. You would say, okay, this is point 1, this is point 2. Okay, and there's various levels of fidelity when you do this, so we'll start with the simplest and sort of add things as we go along. Let's assume that there's no losses to start, okay? So I have H1 minus H2. Which way am I going? Let's do H, the way I should, what did I do? H2 minus H1. The flow goes from 1 to 2. This is minus H loss. There we go. So minus losses. And so yeah, from, okay, so it's H2 minus H1 equals minus head loss plus H pump. Okay? Okay, the head at point 2 and the head at point 1. So the formula for head is just P over rho plus 1 over 2g v squared plus z. Okay, and we're free to pick z to be wherever we want. So why don't we set z equals 0 at point 1. And we'll say this is the Clarkson water tower, which is roughly 200 meters high. Too high? 20 meters high? I don't know. How about, I'd say, yeah, 100 meters high? Yeah, 100 meters high. Okay. Yeah, it could be that. It seems reasonable. I don't know. Okay, so that's that. All right, what do you assume about, so you have to calculate, so if you look at the unknowns here, we're trying to get H pump. That means H1 and H2 have to be known, right? So what do you assume about the velocities at point 1? 0. And velocities at point 2? 0. Okay. Pressure at point 1? 0. Pressure at point 2? 0, right? So that way you know everything about H1 and H2, and you're solving for H pump. Okay, so H1 equals 0. H2 is equal to 100 meters. Okay, so now I have H1 and H2. And so H2 minus H1 is 100. Okay, head losses. Tell me sort of, there's a whole bunch of head losses that we could include in here. Give me, and we're going to start by doing none of them, and then we'll add 1 or 2. Okay? So the head losses we can include is there's a sudden contraction here. There's a frictional loss here. There's a frictional loss here. There's a sudden expansion there. So we could include all of those. Typically, you'll be given, in most of the problems, you'll be given the loss coefficients. Okay, so you'll say the expansion coefficient, the loss coefficient is blah. And so maybe I'll just do, I'll keep out the friction piping losses because those are harder. We'll do those in a separate example. And we'll just do an expansion loss and a contraction loss. Okay, so I'll tell you maybe expansion. K equals 1. And contraction loss coefficient. K equals 1/2. Okay. And the way these things are defined, loss coefficients, if you can't remember, are always defined based on the highest velocity in that little device. So if you think about it, the head loss is equal to K times 1/2 U squared. Okay, so that's the basic idea of head loss for a contraction, an expansion, an elbow, a valve. It's always just K times 1/2 U squared over G. Sorry. There's a 1 over 2G U squared. I forgot the G. Okay. Write that again. And so this is let's just do this problem where you have flow coming in. When flow comes into a pipe, the high velocity is inside the pipe, so you would use the velocity in the pipe. When flow goes out of the pipe, the high velocity is in the pipe, so you still use the velocity in the pipe. Okay? In fact, the velocity out here is essentially 0, and the velocity at the exit is essentially 0. So on both the inlet and the outlet, you use the velocity in the pipe. That making sense? Okay, so 100 is equal to, I've given you Q for this problem, didn't I? Somewhere 1 meter cubed per second. Maybe I'll give you the diameter of the pipes too. I'll give you the area of the pipes just to make it easier. A of the pipe is equal to, it's a big pipe, 1 meter squared. Okay. And so I give you the area of the pipe. So the velocity in V pipe is basically Q over A, which in this case was 1 over 1, I guess, right? Right, I had Q 1 meter cubed per second. A is 1 meter squared, so velocity of the pipe equals 1 meter per second. Okay? So 100 is equal to minus, let's say the contraction was a half, minus a half times 1 squared over 2g. Oh no, I already got the 2 there. Let's just do that right. So always forget the g. So minus k contraction u squared over 2g minus k expansion u squared over 2g, and then plus h pump. U is 1 meter per second. I have Ks, I have Gs, and I can basically now solve for h pump. So I can solve for h pump. And now it asks for the power, right? So this problem asks for the power. And I say, okay, I have the head of the pump. In this case, it's something on the order of, these are small because this is u squared is 1. 1 divided by 20 is 0.05, and the k's are ones. So really, it's just the 100 that matters, right? The change in height is the big thing in here. The little contraction and the little expansion of the exit didn't do anything. So the pump is really just doing all its work against gravity. So I have h pump, and then if I want w dot pump, oh, did I do this wrong? Oh, yeah, right. Is equal to m dot g h pump divided by eta, just from this equation right here. Right? So just take that equation, and I invert it and find w dot pump, and that problem's done. Okay? Okay, that is a head loss problem, and now we just have to do the Moody chart, frictional losses. We'll do that. And how am I doing on time? Yeah, we're doing all right. Let's see what else I have to do before I... Yeah, okay, good. Okay, yeah, good. We got a few more things to do. Let's do just a straight pipe. And I ask you, okay, what is the pressure here at this point? And I tell you the volumetric flow through the pipe. Q is equal to something. I don't know, 0.1 meter cubed per second. And I tell you the diameter of the pipe, D, is equal to, I don't know, 2 centimeters. Okay? And it's flowing water. So this is a water pipe. Okay, and there's frictional losses in this pipe. So now I want to know, the reason that this pressure will be higher than atmospheric is because it has to compete against friction to pump the flow through the pipe, yes? So I write the head equation. This is point 1. This is 0.2. So H2 minus H1 equals minus H loss. Okay. H2 is going to be P atmospheric, which is 0, right? 0 over rho g. Yeah. Plus 1/2 the velocity in the pipe squared, 1 over 2g velocity in the pipe squared, And there's no change in height in this problem, so I don't have to worry about that. H1 is basically minus P1 over rho plus 1 over 2g v squared, and there's no change in height, so I don't have to worry about that, equals minus h loss. And since the velocity at the inlet is equal to the velocity at the outlet, the kinetic energy one sort of goes away. And I just have P1 over rho, oops, I forgot the g again, rho g equals h loss. Okay, so if I can calculate the loss coefficient, the loss for this section of pipe, then I know the pressure at point 1. Okay? And so loss coefficients for a pipe equals the friction factor times L over D times 1/2 1 over 2g u squared. Okay? So that's the formula you need to know. And everything in that formula is fairly simple, except for the F. Yes? The L is the length of the pipe. The D is the diameter of the pipe. G, we know. U is the velocity through the pipe, so I know that. And so the thing I need to get is the friction factor. And that comes from the Moody chart, which I believe is provided on the exam. Let me just show you if I can find it. It's in here. Okay, so here's the Moody chart. It looks like this. That's provided. Yeah. Looks like that. There's two axes. The bottom axis is Reynolds number. The left axis is friction factor. So what you need to know is the Reynolds number. And then there's a bunch of different curves, and the curves are for different roughness pipes. So you would say, okay, here's a table. It would be given of epsilon. Epsilon is the roughness height. And so that would be in some units of distance. Maybe it's concrete. So if it's a concrete pipe, the roughness height, and be careful because it's in millimeters. So roughness heights will always be in millimeters, and your diameter will not. So make sure you don't mess that up. So we need to calculate epsilon over d. And so that's roughness height divided by d. And so let's just say for this example we use concrete. And so that's 0.3 millimeter. Well, let's use 3 millimeters. So that's 3 e to the negative 3 meters. And the diameter I picked was 2 centimeters, which is 0.02. It would have been nice if I picked 0.03, I suppose. Let's pick 0.03. Let's pick 0.03 just to make my life easier. Make it a 3 centimeter pipe. And so the roughness height is 3 to the negative 3 divided by 3 to the negative 2, which is just 0.1. Do that right? I think I did that right. Okay, so that's epsilon over d. That's the non-dimensional roughness height. The Reynolds number, I have to know that, is rho u d over mu. And so if this is water, that's 1,000. The velocity I gave somewhere. Oh, I didn't give the velocity. Darn it. Okay, the velocity is some number. D was 3 centimeters. Viscosity, I think, is 8 e to the negative. Oh, I can't remember the viscosity of water. That's bad. I think it's 8 e to the negative 4. I forget. So I calculate a Reynolds number, and let's just, for instance, say that the Reynolds number comes out to be, we'll do two cases. One will come out to be, Reynolds number comes out to be 3,000. Okay? So then I look up in the chart. at a Reynolds number of 3,000. Here's 2,000, here's 3,000, and I look up epsilon over d. Whoops, I picked way too big of an epsilon over d. And so I'm way up here because the way these curves, you guys remember this? The way the curves are labeled is by epsilon over d. So you pick that curve for your epsilon over d, whatever it is. In my case, I picked the too big of a epsilon, so I have a totally crappy concrete pipe. And let's pretend that I picked a nice copper pipe and I got epsilon over d of 0.01. And I go across and I go to the Reynolds number of 3,000, which is here. And then that's about a friction factor of 0.038. Okay, so now I have the friction factor and I just go from there, 0.038, F equals 0.038. The big transition, the big thing to be wary of when you do friction factors is the Reynolds number of 2,300. If you're below 2,300, you'll have a laminar. I just shut the book. You'll have a laminar profile, which is this curve here. And if you're above 2,300, you have a turbulent profile. And so when you calculate the Reynolds number, you pick the curve depending on whether you're above or below 2,300. And if you're below 2,300, the roughness doesn't matter that much, and so you don't have to worry about it. Okay, so for laminar flows, the roughness doesn't matter. For turbulent flows, it does. Okay, good. A couple other things about pipe flow problems. The one I just did for you was the easiest kind. The easiest kind is you're given the velocity. You're given the velocity. That makes it easy to calculate the Reynolds number. That makes it easy to calculate the friction factor, and then you're good. The worst kind is when you're given the head and you're asked to calculate the velocity, because those are iterative. You have to sort of guess a friction factor, calculate a velocity, plug it back in, calculate a Reynolds number, recalculate the friction factor, and just keep going backwards. I don't know if you remember that. I don't know if they'll do that to you on the exam or not. I don't know if they do that to the exam. I would think that most of them will be the forward kind of problem where you're given a velocity, you can calculate a Reynolds number, you can calculate a friction factor, and then you just go with it from there. Okay? But the backwards ones where you don't know the velocity are definitely much harder. Okay, good. What am I doing here? 8:30. Okay, a couple of important things which I think we should do before I go to the last part, which is they'll ask you questions about fluid measuring devices. And so there's two important ones. There's actually maybe three important ones. This pen is pissing me off. Measuring devices. Okay, so the most common fluid measuring devices are the pitot tube. A Venturi. And what's the other one called? Oh, crud. Well, let's go with those two until I can remember the third one. I don't think they're going to ask you about a rotometer. I think those are these are the two most important, pitot tube, Venturi. A pitot tube is essentially a stagnation pressure device. So you take a little piece of metal and you just bend it and stick it straight at the flow. So the flow goes straight at the pitot tube. The pressure, the flow stagnates on the front of the tube, and then you use Bernoulli to figure out what the velocity is. So that looks a little bit like this. Okay, so here would be, yeah. Let's say I wanted to know the flow, the velocity in a pipe. I drill a hole through the pipe and I put a little tube that looks like this in it. Okay. That's also the thing that you see on the side of an airplane. When you go in and you look left, you'll see the pitot tube sticking out of the side of the airplane. Okay. And then at roughly the same location, I put a tap on the side of the wall. Okay, so I put a pressure tap there. And so the nice thing for them to do is to combine this with the manometer problem. Oh, why does it do that? don't know why it does that. I think I have to be there. It doesn't like when I scribble. Okay, so I have this pitot tube combined with the manometer problem. The flow is coming down the pipe. And the idea is along this streamline we can apply Bernoulli. Okay, and so we say, okay. And the other idea of this is that the pressure, yeah, okay. Okay, so let's see, we go, blah, 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 blah. Yeah, okay. P1, P2, P1 minus P2. Bernoulli's equation, sorry. Blank, 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 blank. And there's no gravity, so I'm going to leave that out. But Bernoulli would normally have this, right? Oh, crud. It's just like the head equation plus z. Right? Equals, this is P1, V1, Z1, P2. Okay? And I don't have any, I'm not going to worry about gravity. Maybe it's air, so I don't have to worry about that effect. The velocity at point 2 is 0 because it's stagnated. It ran into the front of this pitot-static tube. Okay, so the velocity at point 2 equals 0. And then I say, okay, this should be over rho g, which I forgot. There we go. P2 minus P1 over rho g equals 1 over 2g V1 squared. And so if I can measure the pressure difference P2 minus P1, then I can, and maybe I will, let's just do this a little bit better. So, whoops, makes it a little bit more obvious. There we go. Okay, and then I'll put P1 over here just to make it a little bit more obvious. There, okay. And then you're given, you read the manometer, so you're given that height. And so basically you say, okay, in a pipe there's not much gradient in pressure across the pipe, so the pressure P1 is essentially the pressure on the manometer on the left side. And the pitot tube measures the stagnation pressure where the velocity is 0. So that manometer is going to read P2 minus P1. So you calculate from the manometer the pressure difference, you multiply by 2g, or well, actually you would divide by rho, multiply by 2, and take the square root. And so you get V1 is equal to the square root of P2 minus P1 over rho. And if you have the manometer reading, P2 minus P1 is just delta rho GH. So I'll do a quick hydrostatics problem. And this rho is the rho of the delta rho is really the difference in the two fluids, the manometer fluid and the fluid in the pipe. And the rho is the fluid in the pipe. So this is the pipe fluid. And so the delta rho comes from the fact that you have this section and that section. Okay, that's the hydrostatics part. You guys, we already talked about the hydrostatics part, so I'm not too worried about that. I just wanted to show you the pitot part. Okay. Okay, so that is a pitot-static tube. And the other important sort of fluid measuring device is something called a venturi, which is nothing more than a contraction. And we take a manometer reading from here to here. Okay, if there's no flow through the pipe, there'll be no pressure difference because nothing's happening. But as there's flow through the pipe, because of conservation of mass, the flow here has to be moving faster, right, at the center of the contraction. So you have a flow speeding up. The flow speeds up by Bernoulli. That means the pressure goes down. And so now we can figure out basically based on the manometer reading, what the speed is in the pipe. So that would look a little bit like this. We call this point 1, call this point 2. We call this area 1, call this area 2. So we have U1 times A1 equals U2 times A2. Yeah. And we also have P1 over rho G plus 1 over 2G U1 squared. And I'm going to leave off the gravity again. Is equal to P2 over rho G plus 1 over 2G U2 squared, right? Okay, good. And the short answer to this is that if I measure P1 and P2, I measure the pressure difference, right? Now I have two equations and two unknowns, and I can just solve for U1 and U2. Okay, so that's the short answer to it. But we can go the longer way. We just say, okay, P1 minus P2 over rho G equals 1 over 2G P1 minus P2, yeah, U2 squared, whoops, minus U1 squared, right? And now I can plug in that, I'm going to calculate the velocity at the contraction, so right at the throat. So I'm going to calculate U2. So P1 minus P2 over rho G equals 1 over 2G. U1 is basically U2 times A2 over A1. What did I just do? I messed that up, didn't I? I want to get rid of the U1. U2, what am I doing? Erase, fix. Getting rid of the one. This is U2 squared minus U1, which is U2, crud, A2 over A1, quantity squared. Factor out the U2 squared, divide, take the square root, and you have the velocity. Okay, so that's another. Everybody got that? The last part of the steps is just to write this as and now I just divide by that leading coefficient, which I have I've known all of it, and now I can solve for U2 squared, and I take the square root and I have a velocity. So that's a very common velocity measuring device, a Venturi. Okay, good. I think we're almost done. I think the last thing I want to talk about is similarity things. Yeah. Good. So similarity / dimensional analysis. This is the Buckingham pi theorem. That's not spelled right, is it? So Buckingham pi basically says that if you have, let's say here, something, typically I would write this as like some property, maybe power, I'm just making up an example, is a function of a bunch of things, rho, u, D, maybe it's a wind turbine problem. So the wind velocity, the density of the air, the diameter of the wind turbine, the number of blades, the angle of attack of the blades, the rotation speed of the wind turbine, right? And so there's a relationship between, I've written down this general functional form, but there's only certain combinations can work because there's only certain combinations of these dimensional quantities that can give me units of power, right? And so the idea is that the number of pi groups is equal to the number of independent variables minus the number of fundamental units. And so the fundamental units are mass, length, time, temperature, okay? Okay, so not every problem has temperature in it, so sometimes you'll have temperature, sometimes you won't. But most all problems have mass, length, and time, okay? So in this particular problem, I don't have any temperature variables. I have pressure, I have power, which has units of mass, length, and time in it. Density, mass and length. Velocity, length and time. D, which is length. N, sometimes they'll throw in an N, which is just the number of blades. Number of blades is an integer. It's it's unitless. So in some sense, N is already a pi group. I don't have to do anything about it. It's a non-dimensional group. Alpha is another one that'll sometimes be thrown in there. Alpha is an angle of attack. Angles are radians. Radians are unitless. So a radian is really a ratio of an arc length to a radius. So it's unitless. And omega in this is radians per second. Radians are unitless, so it's really 1 over time. Okay? So those are all the units. And so I'm expecting to get, if I have 1, 2, 3, 4, 5, 6, 7 independent physical properties, and I have 3 fundamental units, I should get 4 pi groups. Okay. Actually, of most of the problems I saw in the exam are using the standard pi groups that come out of fluid mechanics. So we'll talk about those first before we get into the details of calculating pi groups. Most of the time you can get away with just knowing the pi groups without having to actually calculate the pi groups. And so the most standard ones are the Reynolds number. That one is like, people in solid mechanics like to joke that if you go to a fluid mechanics conference, you can sit in the back and just raise your hand at the end and say, well, what's the Reynolds number? Because that's everyone ever does in a fluid mechanics conference. Is then in the middle of the talk, they raise their hand and ask what the Reynolds number is. This is, if you want to look like a fluid mechanics professor, that's what you do. Okay, good. Got that. Other ones is a Mach number, which is the velocity over the speed of sound. And the speed of sound is equal to the square root of k, which is Cp over Cv, which is 1.4. R, which is the ideal gas constant divided by molecular weight, right? So R is equal to, and for air it would be divided by 28.97, I think. Something like that. And so that's R and then T. Okay? Typical values for the speed of sound for atmospheric conditions are 330 meters per second. But the speed of sound varies with temperature, so that's just at 30 Kelvin, or at 30 Celsius, it's around that. Okay, so Reynolds number, Mach number, those are the most important non-dimensional numbers. Sometimes they may ask you about a free surface problem, so an open channel flow, and I haven't talked a lot about open channel flows, but the most important number for open channel flows is the Froude number. U squared over GD. Okay, some other ones that you'll definitely run into is other non-dimensional numbers is the coefficient of drag, right? So that's non-dimensional force. Force divided by 1/2 rho u squared. Coefficients of drag, if it's a blunt object, the area that it's used will be the cross-sectional area. So for blunt objects like cars and squares and stop signs and all sorts of stupid stuff like that, it's the cross-sectional area. For streamlined objects like flat plates, wings, those are two streamlined objects, it would be the plan form area. Okay, so the definition of the area depends on what object it is. Okay, CD is like that. Okay, so here's a typical question which I could do without having to figure out the non-dimensional groups, which is just to say, you're testing in a wind tunnel. This is definitely a question on the exam. And so basically the force on an object is a function of the velocity, the size of the object, the viscosity of the fluid, the density of the fluid, right? And without doing any work, I'm going to pick, I see that I have 4 quantities, or 5 quantities, right? 1, 2, 3, 4, 5. And I have 5 quantities, and I have 3 fundamental units. I have mass, length, and time. There's no temperature in this problem. So I'm expecting 2 non-dimensional groups, right? And I will pretty much in fluid mechanics, you're pretty safe to always pick U, rho, and D. Those are usually the most common choices for repeating variables. And so I say, well, what am I going to get when I non-dimensionalize F using a length scale, a rho, and a U? Well, that's basically non-dimensional force. That's going to be like a CD, okay? And so, and D, you know, I haven't listed all the geometric parameters, but mostly we'll just say that this is the non-dimensional version of this without doing much work is CD is a function of mu divided by rho, u, and d, which is just the Reynolds number. Okay? So that's the non-dimensional version of that equation. You've gone from 5 dimensional quantities down to 2 repeating variables. 5 minus 3 is 2. Okay? So CD is a function of Reynolds number. And now I say, okay, you want to test like an airplane, and you have Clarkson's wind tunnel, which has about a 1 meter by 1 meter cross section, I guess, something on that order. And so you're going to have to scale down the airplane. Yes, it's not going to fit. This is pretty obvious. And so let's say we use a 1/10 scale airplane. I don't know if that actually would fit. I don't really care either. Maybe it's a model plane. I just shrunk it. What Reynolds number should you test at? So no, sorry. Yeah, no, sorry, that's not the question I want to ask. What velocity? Okay, so the idea with the scale testing and similarity is to keep the non-dimensional groups the same. Yeah, that's the idea. Is keep the non-dimensional groups the same, and then your non-dimensional relationship will be the same. And so I go over here and I say, okay, Reynolds number is equal to rho full scale, u full scale, d full scale, divided by mu full scale. And unfortunately, we can't change air, so air stays air. And I want to keep the Reynolds number of the full scale thing equal to the Reynolds number of the test. Reynolds number of the model, u model, d model, over mu model. Okay, so it's air. So rho model and rho full scale are the same. Mu model and mu full scale are the same. I have air in the wind tunnel. I have air around a real airplane. And so I just cancel that out. Those are the same. And then I go down and I say, okay, let's solve for the speed in the wind tunnel. U model divided by u full scale is equal to d full scale divided by d model. Okay? And so D full scale divided by D model. In this example, I made a 1/10 scale model. So that means that D model is 1/10 of D full scale. So this number comes out to be 10. And this is often something that students think is odd. You shrink the model, and you have to go 10 times faster. Yeah? You would think you'd shrink the model and you would go slower, but to keep the Reynolds number the same, you shrink the model. If you shrink the model by a factor of 10, you have to increase the velocity by a factor of 10. Okay? And so that's a typical Reynolds number scaling kind of problem. I think I'm good. What else do I have to tell you? I'm getting tired. Yeah, okay. CD, I guess you could say then, given that you tested in the wind tunnel and you got a certain CD, what would be the CD on the full scale? The same, right? And so now you have the full scale velocities, and you can just basically plug in the full scale velocities and get the CD. Now the tricky part of that is first you've got to calculate CD from the model. So you take the drag from the wind tunnel, divide by 1/2 rho u squared, where u is the velocity in the model, and a of the model. That gives you CD. Then you remultiply by that with all the full scale stuff, and that gives you the force in the full scale. Okay? Is that clear? I think that's good. I think I'm done too. You guys are done. I'm done. We're all done. Yes? Okay. Good.